All right, hope you guys can all hear me okay. I put a link in the chat if you didn't, for some reason, didn't get the test review worksheet that I handed out last week. So we're going to start with the 2016 FRQs. So just work through most of the FRQs, and then when we get to the multiple choice, I'll just kind of jump around between different problems. And if you have any questions, feel free to put your question in chat box, or you can unmute yourself and just ask the question. All right. Okay, so number one, company produces and sells chili powder. Company's weekly profit on the sale of X kilograms of chili powder is modeled by the function P. P of X is 4.48X plus 1.4X squared minus 0.5X to the 2.8 minus 270, where P of X is in dollars and X is between 0 and 80. Okay, so part A, find the rate in dollars per kilogram at which the company's weekly profit is changing when it sells 32 kilograms of chili powder. And we're looking for, we know that P of X is in dollars, but we want to look for how the profit is changing. So that should indicate that we're asking about the rate of change. And then is the weekly profit increasing or decreasing? Okay, so for part A, we know that we're going to have to get to P prime of 32. So this is calculator section, so we can make the calculator do the work for us. So under Y1, I'm going to go ahead and enter in that 48X plus 1.4X squared minus 0.5X to 2.8 minus 270. And once you enter that in, math 8, d over dx, and then I already have Y1 storing my P of X. So if I do alpha Y equals, alpha trace Y1, and then plug in 32. Okay. And once you enter that in, okay, we should get 65.920. Right? And then since P prime is positive, we know the company's profit is increasing when it sells 32 kilograms of chili powder. Okay, part B, how many kilograms of chili powder must the company sell to maximize its weekly profits? So anytime we see the word maximize, we know that there's some sort of an extreme value theorem going on, and we basically want to find when P of X is going to be at its greatest value. Okay, so if we think about extreme value theorem, we think about how we want to include our endpoints, and we know the endpoints will be 0 and 80. And then we also need to find critical points, and that is where we set P prime equal to 0. So we've been working with P prime, we plugged 32 in for P prime, but now we're going to set P prime equal to 0, and then find those critical points. And once you find those critical points and the endpoints, we'll insert them back into P of X, and then we'll compare the values. Highest Y value will be the absolute max, and lowest will be the minimum profit. Okay, so part B, we know we have to find our critical points. We know the endpoints already. We know we're going to test 0 and 80, but we also want to set P prime to go to 0. I'm going to just find P prime by hand here. So power rule 48 plus 2.8x minus, and then if I do 0.05 times 2.8, I get 0.14 x to the, and I subtract 1 from 2.8, right? When we do power rule, we bring down the exponent and we subtract 1 from the exponent. So 2.8 minus 1 is 1.8. And then we know that constant will go to 0. Okay, so we have our P prime. Critical points is found by setting our P prime equal to 0. Now, this is not something that we can solve by hand. This is not a quadratic, 1.8. So let's make the calculator do this for us. So we can graph this and then look for the x-intercept. Okay, so let me put this in the calculator. So I'll go to y1. Minus 0.41. Okay, let's see, under window, I know I want to go from 0 to 80 because those are my x values. So under window, x-min, I'll say 0. Under x-max, I'll go to 80. I have my values up here in the hundreds, so I'm just going to kind of estimate that maybe negative 200 and 200 should allow me to see something where, let's see what that looks like. Okay, so we're just looking for the x-intercepts here. Let's see where this one is. Okay, hold on, 48 plus 2.8x. Oh, okay, 0.14. I think I entered in wrong. Okay, so let me do second trace 0. Enter. Scroll to the other side, hit enter again. There it is, 58. So we know there's critical point at 58. There's only one critical point, so we'll test 58.358, and we'll test 0, and then we'll test 80, and we'll insert them all into the P of x equation and see which one produces the largest value. Okay, so I want to do P of 0 because that's an endpoint. I want to find P of 58.358 because that's the critical point that I just found, the x-intercept that I just found. And then also P of 80, that's my endpoint. So I have it stored under y2. I have that equation, P of x stored under y2. So if I do alpha trace y1, okay, if I plug in 0, I'll get 48. Oops, y2, sorry. I have it stored under y2. Okay, so negative 270, 58, then endpoint 80. Okay, so then between these three, our largest value is 2893. So we can say the company needs to sell 58.358 kilograms of chili powder to maximize the profit at 28.93 and 4 cents. Part C, company plans to have a one-day sale on chili powder. Management estimates that T hours after the company stores open, chili powder will sell at a rate modeled by the function given by S sub T, kilograms per hour. So this is the rate. Based on this model, estimate the amount of chili powder in kilograms that will be sold during the first 5 hours of the sale. So we want to get from kilograms up to the amount of kilograms. So we're going to take this rate and we're going to accumulate it over a 5-hour period. So that's just an integral, right? Integral will take the rate unit and make it rise up to something in terms of kilograms. Okay, so this is go math 9. So we do math 9 from 0 to 5, plug in your S sub T equation. We should get 11.433 kilograms. All right, part D, using the function S from part C, find the value of S prime of 3. Interpret the meaning, value in the context of this problem. So again, this part is not too difficult. We just make our calculator do the work for us. We already have S sub T stored in our calculator. We'll do math 8, and then plug in the 3, and that'll give us kilograms per hour squared, because S sub T is in terms of kilograms per hour. And then if we find S prime on top of this, then it'll be kilograms per hour. And so if we get a negative value, we know that the rate is decreasing, right? Rate is decreasing. If we get a positive, that means the rate is increasing. So we know that something is at the second derivative level. We want to be able to use these words, rate increasing or rate decreasing, to help the grader help the grader see that we can earn those all the points there. Okay, number 2. Store tracks the sales of one of its popular board games over a 12-week period. The rate at which games are being sold is modeled by the differentiable function g, where g of t is measured in games per week, and t is measured in weeks for t between 0 and 12. Values of g of t are given in the table for selected values of t. Approximate the value of g prime of 8 using the data in the table. Show the computations that lead to your answer. So again, this is calculator active for the first 2 problems. So we have something, we have our table in terms of g. We want to get down to g prime. We know g prime is at the derivative level, but it's asking us to approximate, so we can't use calculus. So the way that we can involve approximation of a derivative is to use slope. So we find the closest points between 4, 8. So the closer we are, the better approximation that we can get. So our best data to get our approximation is using the week 6 and week 10. So we just do change in the change in games per week divided by the change in weeks. Okay, so we say G of 10 minus G of 6. So change in games per week divided by the change in weeks. Now G of T is already in terms of games per week. So if we find the rate of change of that rate, it'll be games per week. So it'll be games per week squared. Right, that's our approximation of G prime of 8. Part B, approximate the value of the definite integral from 0 to 12 of G of T using a Wright-Riemann sum with 4 subintervals. Explain the meaning in the context of this problem. So, well, Wright-Riemann sum is pretty straightforward, right? We can just do width times height, subtract each of our weeks to get our width. So 3 minus 0 is 3, 6 minus 3 is 3, 10 minus 6 is 4, 12 minus 10 is 2. And then we find the appropriate height for the right subinterval here. So width is 3, height is 450. Right, width is 3, height is 900 for the third rectangle. Width of 4, height of 2100. Width of 2, height of 2400. And we just go through and we add our areas up. And we get 17 to 50. Now our units will change, right? So we started with games per week, but we're going to accumulate games per week over the number of weeks. So essentially we're doing games per week times weeks. And if we multiply these two units together, essentially we have G of T, which is games per week, multiplied by dt, time in terms of weeks. We multiply these together, our week units will drop out and we're just left with games. So this represents the total number of games sold over that entire 12-week period from week 0 to week 12. Part C, one salesperson believes that starting with 2,400 games per week at t equals 12, the rate at which games will be sold will increase at a constant rate of 100 games per week. Based on this model, how many total games will be sold in the 8-week time between week 12 and week 20? Okay, so what we can do is we can create a model that will represent the rate that the games will increase by. So we're going to create a point slope form for our rate R of t. We're going to build that R of t, and then we're going to accumulate that over the 8-week period between 12 and 20, because we don't have the data from 12 and 20, so we're going to create a model for our prediction of what could happen in the next 8 weeks. Okay, so we're going to start with the data that we have. We have week 12. We have the rate of 2,400 games per week. And the slope that we want to use is 100 games per week. So this is our slope for our rate equation. Okay, so we have our order pair and our slope. And then we can build our R of t equation. So instead of y minus y1 and x minus x1, I'm doing r minus r1, t minus t1. So r minus 2,400 equals the slope 100 times t minus 12. I'm going to solve for r. Okay. And remember, r right now, R of t is in terms of games per week. So we're going to take this rate and we're going to accumulate this games per week over the next 8-week period. So we're just using this trend to help us estimate how many games could be sold over the next 8 weeks if we're just using this constant data, or this data, which is a constant, games per week. Okay, so once we have that RT equation, and we know that we're going to accumulate this rate over the next 8-week period, we can put this in the calculator. Math 9 from 12 to 20, 100 times x minus 12 plus 2400, and then that will get us to 22,400. Okay, another salesperson believes that the best model for the rate at which games will be sold in 8 weeks between 12 and 20 is given by this MFT, games per week. Based on this model, how many total games will be sold during this period? So we're still going to use integral, but we're using a different model here. So we're going to do integral from 12 to 20 of MFT. Rather than using this constant slope, we have something a little bit more complex, but ultimately it's still trying to do the same thing. It's just trying to predict how many games can be sold between weeks 12 and 20, whether using this model or using this model. Okay? But this one we can just enter directly into our calculator. So 15,784 is based on this model. This will be the total number of games sold between 12 and 20. So. Okay, next up, number 3. A function f is defined on the interval from -5 to c. C is some number. We just don't know what that number is, but it could be 3, it could be 5, it could be 4. We just have to hold on to that constant there. The graph of f, which consists of 3 line segments in a quarter circle with center -3, 0. So this is the center of the quarter circle, the imaginary circle here that we don't see. And radius 2. So they're just describing the dimensions and the location of the quarter circle. Okay, find the average rate of change over the interval from -5 to 0. So average rate of change. So we want to find the change of f. So that's slope, right? So we're just going to do slope between endpoints here. Okay. So f of 0 is 2, f of 5 is 0. Sorry, f of -5 is 0. All right, part B, between -5 and 0, let g be the function defined by g of x is the integral from -1 to x of f of t. Find the x-coordinate of each point of inflection. So let's understand what that relationship is between g and f here. So if we know that g is the integral from -1 to x, we know that g prime must mean the derivative of this, and the derivative of this notation is simply just f of x, right? So g prime is f of x. So this is basically the g prime graph, right? Because we've established that relationship now, that f is g prime. So if this is the g prime graph, If this is the derivative graph of g, then if I want to find the point of inflection for the g function, I just have to be able to know how to pull that from a graphical perspective, right? If we're looking at the first derivative graph, the point of inflection that represents that g of x function is going to be the peaks and valleys, right? The hills and valleys of your g prime graph are the points of inflection. Okay. So the way that we want to be able to say this, though, we don't want to say peak or valley. We really want to indicate that the graph of g prime or f changes from decreasing to increasing, right? Or from increase to decrease. So the fact that it changes from decrease to increase of the slope of the slope of the g prime graph is what indicates that there's going to be a point of inflection. Okay. So point of inflection occurs at x equals -3. We know this point of inflection for our g graph because g prime changes from decrease to increase at x equals -3. And then we know there's point of inflection at x equals 0 because g prime changes, or g prime or f changes from positive slope to negative slope, or changes from increase to decrease. Part C, find the value for which the average value of f over the interval is 1/2. So this one is working our average value theorem a little differently, because usually with average value theorem, we know what the endpoints are, and we plug in, and we're actually finding out what the average value is. So here it's a little bit different because we do know what the average value is, but we don't know what the end bound is. So we have to kind of work our way and work backwards and figure out what that C value is. Okay, so here's my average value theorem. Okay, my A and B values are -5 and C. So 1 over C minus a -5. Integral from -5 to C of f of x dx. So we know when all this is said and done, our average value is equal to 1/2. Okay, so what we can do is we know what we can do. We can do with this. We can replace this with a number that we're going to find by doing displacement, right? So between -5 and C, we're just going to figure out the area and displacement between the graph and the x-axis, and then we can find all those numeric values and plug it into this space, and then that will give us an algebraic way to eventually get down to solving for C. Okay, so let's revisit what shapes we have here. So we have a quarter circle below the x-axis. We know a circle area is pi r squared, so quarter circle is 1/4 pi r squared. Again, they say that the center of this quarter circle is here. We know the radius is 2. Okay, so 1/4 pi r squared, so 1/4 pi times 2 squared. And 4 pi divided by 4 is just going to be pi. Negative because it's below the x-axis. So this quarter circle is -pi. And then this here, triangle below the x-axis, 1/2 base times height, 1/2 1 times 2. Oh, that's going to be a -1. And then here, 1/2 base times height, 1/2 2 times 2. 4 over 2 is going to be 2. And this this we have to just understand that we don't know what that number is, but we do know that is some C value. So let's just think of this as that the width of my triangle here in the first quadrant, right? The width is C, my height is 2, and then 1/2 C times 2 is just going to be C. So the area of this will be just C. I know that's something that prefer to see a number there, but we'll just treat this C like any other number and just go down the process of finding the area. So we have displacement here, negative pi minus 1 plus 2 plus C. So that can go in place of this. And now I'm just down to an equation that I can work towards solving for C. Right? Okay, so if I clean this up here, I'll get 1 minus pi plus C. I'm going to put this in the denominator under this parentheses here, so then I can maybe cross multiply. Because my whole goal now is to solve for C, right? It says find the value of C. That's my goal of part C. Okay. Now if I cross multiply here, right? Combine some like terms here. Let's see, did I mess up 2? Oh, sorry, this is a positive 2, not a negative 2 here. Okay, I'm going to move the C's together on this left side here. So 2C minus C is just going to be 1C. And I get 5 minus 2 plus 2 pi. So there's part C. Part D, assume that C is greater than 3. The function h is defined, h of x equals f of x over 2. Find h prime of 6 in terms of C. So, all right, let's find, we know that we have to get to h prime of 6, so we have to build our derivative. I'm going to say h of x is f of x over 2. I'm going to think of that as 1/2 x. Right, just to get myself ready for chain rule there. So if I want to find h prime of 6, I first have to get to h prime of x. To get to h prime of x, a little bit of chain rule. There's the outside, inside portion here. My outside is the f times my inside's derivative. So the derivative of 1/2 x is 1/2. Okay, a little bit of chain rule there. All right, next up, replace every x with 6. Well, there's only one x here. Replace that with 6. 6 over 2. Okay, f prime of 3. So we're trying to figure out what is the slope of the f graph at 3. Now they tell us that C is greater than 3. So we know that 3 is going to have to land somewhere here, right? So let me just assume that is 3. Sorry, assume that's 3, right? So basically, to figure out, if we can figure out the slope of this line segment, then we have the slope of this graph at 3. So if we think about slope, slope is just rise over run, right? So I got to go down 2 over C. So -2 over C, that's my slope. So the slope of my line segment is just down 2 over C. I can reduce that to just make it negative 1 over C. All right, number 4. Let S be the shaded region in the first quadrant bounded by the horizontal line, y equals 3. So now we're moving, sorry, number 3 was non-calculator. This is also non-calculator here. Okay, find the area of S when k equals pi over 3. So now I want this to be pi over 3. And we're going all the way to pi over 2. Okay, so area is just the depth integral of the top graph minus bottom graph, right? Top is sitting at the 3, the bottom is sitting on that sine 3 sine of x. Okay, so top minus bottom, that's just area. 3 minus 3 sine of x. Okay. No squared, no pi. This is not volume. We're not rotating anything. I know area formula feels like there's something missing, but it's just really just top minus bottom, and that's it. So don't include any squared as part of your formula. Okay, so now we can just go through. Remember, this is non-calculator, so we got to work this out by hand. We got to work this out. 3 is 3x, 3 sine x. Sine becomes negative cosine. I'm sorry. Sine becomes negative cosine. The two negatives cancel out to be positive. So we get the antiderivative is 3 becomes 3x. Negative 3 sine x becomes positive 3 cosine x. We can plug in our upper and lower bound. Upper bound first. Pi over 2 and for all the x's. So 3 times pi over 2 plus 3 cosine of pi over 2 minus big parentheses. Repeat the same process for the lower bound. 3 times pi over 3 plus 3 cosine of pi over 3. Now, we can't leave our answer like this. Okay, we got to go one step further. We have to resolve these unit circle values. So it's important that if you're shaky with unit circles, make sure that you review your unit circles. Right. If you leave your answer in this form, you're going to get at least 1 point taken off because you did not go far enough. Okay, so pi over 2, that's just a number. Cosine of pi over 2 is 0. 3 times pi over 3 is just minus pi, and then cosine of pi over 3 is 1/2. Now, if you want to stop at this point, that's fine because you've already resolved all your unit circle values. So this is fine, but you can also go a little further and clean up a bit more. But if you leave your answer in this form, that will still earn you full credit right here. Part B, the area of S is a function of K. find the rate of change of the area of S with respect to K when K equals pi over 6. So we can say for part B here, sorry, part C, area of S is a function of K. So K is our independent variable here. And we can say the integral from K to pi over 2 okay, so this is our starting point. This is our area with respect to K. Find the rate of change of the area. So we're trying to find, we know rate of change is talking about A prime. So we got to get down to A prime. So A prime would be the derivative of this. And we know the derivative of an integral is going to have to go through a second theorem. But if we want to go through second theorem, we prefer that variable to sit up top. So I'm going to rewrite, put that K up in the make that K go to the upper bound. But if I want to swap the bounds, I do want to make sure I balance my expression out with a negative in front. So I want to find the derivative of an integral. So now this is in the form where I can apply second theorem. I know derivative integral notations will cancel out. The upper bound will get inserted in for the x. The lower bound, that number will go away. That constant will go away. I'm just left with -3 plus 3 sine of k. So that's my A prime. My derivative A prime is just going to clean up to -3 plus 3 sine k. And now I just want to find what is A prime of pi over 6. Replace pi over 6 in for k. So -3 plus 3 sine of pi over 6. I can't leave my answer in this form. I got to go one step further. I got to resolve this unit circle value. So sine of pi over 6 is 1/2. So you can leave your answer like this, -3 plus 3 times 1/2, or you can go all the way down to -3/2. But we have to go one step further beyond this. We can't just stop here. Okay, part C. Region S is revolved about the horizontal line, y equals 5. So let me draw the diagram again. Okay, so there's my shader region. I'm rotating this about the line y equals 5. Now the axis is clearly off of the shaded region. There's a gap, and because of the gap, and we're doing rotation, we know this is going to have to be Washer method, right? Okay, so Washer method requires us to draw two radius. One radius will extend from the dotted line all the way to the furthest boundary of our shaded region. That's big R. And small radius will be from the dotted line to the closer of the two. Okay, so big R of x, top minus bottom. The top is sitting at the 5. The bottom is sitting at the 3 sine of x. And then your little r, top is sitting at the 5, the bottom is sitting at the 3, so just 5 minus 3. Okay, your volume formula is just pi integral from k to pi over 2, because that's the left and right bound of our shaded region. Now keep in mind, whenever you're doing bounds, don't look at your axis, just look at your shaded region. Your bound is just for your shaded region. Doesn't matter how far away your axis is, the axis has no influence on the bound of your integral. Okay, and then we do big radius squared minus little radius squared. Oh, they say when k equals pi over 4, so I need to replace k with pi over 4. Okay, replace r of x with 5 minus 3 sine of x, quantity squared. Little r of x, quantity squared. Okay, number 5. I want to make sure I have enough time for the multiple choice section, so I'm just going to kind of walk through the key here. Okay, so between 0 and 24 hours, temperature inside a fridge is given by W that satisfies differential equation, W dW dt equals 3 cosine of T over 2W. W is measured in Celsius, T is measured in hours. Write an equation for the tangent line. So tangent line means we got to gather our order pair and slope. Typically, we experience tangent line in terms of y and x, but for this problem, instead of x, we're going to do t minus t sub 1. Instead of y, we're going to say w minus w sub 1. So order pair is 0, 3. Instead of x and y, I'm going to call that t and w. My slope comes from the differential equation, so insert 0, 3 into my differential equation. Replace t with 0, replace w with 3, and I get 3 times cosine of 0. Cosine of 0 is 1. So 3 over 6 is 1/2. So here's my slope. Here's my order pair. Get w by itself. So I get 1/2 t minus 0 plus 3. This is my tangent line equation. Now I can use this tangent line to do approximation. I want to do approximation at 0.4 hour. So plug 0.4 in for t. And you can leave your answer like this. You don't have to get all the way down to 3.2. You can just leave your answer in this form. This is non-calculator, so any equivalent unsimplified answer is as good as simplified answer. Okay, so this is fine. Part B, find a particular solution for a different differential equation. We're going to go through our process, cross multiply, and then we want to get our W's together on one side, our T's together on the other side. Now, once you cross multiply, you're not guaranteed that you're going to get full separation. But in this case, I like to make sure that my dW dt are lined up. And then I look to see, do I have anything out of place? My T's are together. My W's are together. Really, the only thing that's out of place is that 2. But if we look ahead, we know that if we do power rule, W squared over 2 will cancel out that 2. So you can divide that 2 over. I'm just looking ahead and seeing that, okay, if I just do power rule here, I can get the 2 to cancel out without having to go through that additional step. So moving that 2 is fine. I'm just looking to see, maybe I can just get that 2 to go away once I apply power rule. Okay, so I have full separation, no need to move anything. I'm going to take the integral of both sides. Power rule on the left. Just trig on the right. There's no need to go through u substitution because I don't have anything inside the parentheses. If I had like 1/2 t or 2t or 3t, then I do want to go through u substitution because I want to keep track of that coefficient that's going to come out of that process. Okay, so w becomes w squared over 2. The 2's cancel out. Cosine becomes sine. Don't forget, plus c shows up. 2's cancel out. I'm left with w squared equals 3 sine of t plus c. Now we have 2 things left to do. We got to solve for c. We got to solve for w. Now students sometimes would ask me, wait, what do I do first? Do I solve for w or do I solve for c? Or do I solve for x first? Or sorry, do I solve for c first or do I solve for y? And the answer to that question for me is it depends. If I feel like C is an easy one to solve at this stage, I'm going to go ahead and solve it. But if I feel like I can wait to solve it, then so typically if I see a square and if I'm expecting a square root, I typically want to get that c solved before the square root comes up and it becomes harder to solve for c with the square root. But typically if I see natural log in the process, I typically wait for that c, but it really doesn't matter as long as you solve for both. Doesn't matter the order that you solve them. Okay, so I'm going to replace 0 in for t, 3 in for w, just solve for c, get that out of the way. So 9 is equal to 0 plus c, c equals 9. Replace 9 in for c. Now I'm just one step away to get that w by itself. Take the square root. Now if I take the square root, there's plus and minus that shows up. Now that indicates these are two solutions. We only want one solution. We only either want positive square root or negative square root. And the way that we tell is we look at the order pair. Okay. If we look at the y value, okay, whatever the sign of the y value is, then that's the sign that I want. Okay. So since 3 is positive, then I want to choose the positive square root. Now, if that y value was negative, then I would choose the negative square root. I need to be able to have an equation where if I plug in that x value, I can get that corresponding y value. Otherwise, this order pair will not live on the function. We want an order pair that's going to live as an order pair on the function that we provide. All right, part C. The temperature in the kitchen remains at a constant 20 degrees Celsius between 0 and 24. So this is talking about the temperature in the kitchen, okay, the room temperature. The cost of operating the refrigerator accumulates at a rate of 0.001 per hour for each degree that the temperature in the kitchen exceeds the temperature inside the fridge. Okay. Because there's going to be energy that needs to be energy that's going to be used for each difference that the fridge has inside the fridge versus the temperature in the kitchen. Right, but do not evaluate an expression involving an integral that can be used to find the cost of operating the refrigerator over the 24-hour period. So we don't have to solve it, just have to set it up. Okay, so we know that W of t represents the temperature inside the fridge. So if we say 20 minus W of t, that will give us the difference between the temperature in the kitchen versus the temperature inside the fridge. And then each difference is going to have that factor in that cost of 0.001. But for every, we want to accumulate all the difference between the temperature inside and outside the fridge over that 24-hour period. So we can whatever this value is, this will accumulate all the changes in temperature, difference in temperature between the kitchen and the fridge, and we're going to take all that difference, multiply that by $0.001 to get the total cost over that 24-hour period. Okay, part A, we have a piecewise function here. Is the function continuous? Okay, we got to step through continuity conditions here. So here, f of 1 is equal to 7. We choose the order pair. So continuity conditions are, does the point exist? Does the limit exist? And does the point live where the limit lives? So we find that equal sign there, plug 1 in for x, and we get 7. So that's our order pair. Now, if I see less than and greater than, that means I have two distinct functions split on either side of my x value. So I need to do one side limit. I need to figure out where is this graph headed from the left side of 1, and where's the graph headed from the right side of 1, and see if those numbers agree. Okay, so if I plug 1 into both of the expressions, I get 7. So great, my limit exists. So the whole, or that whole, would be at 7. But then the third condition is saying, does the limit live where the point lives? So we're just going back and comparing the numbers. So here, the graph meets at a y value of 7. Here, the point lives where that limit lives. So everything is connected. So since my ordered pair lives where the limit lives, my function is continuous at that singular point at x equals 1. Part B, find the absolute minimum value and the absolute maximum value on the closed interval from -2 to 2. So we know there's a critical point at 1 because that could be a relative max, could be a relative min. But we also want to find critical points for this function and for this function, and see if there's anything hiding between -2 and 1 for this function, and see if there's any critical point hiding for this graph to the right of 1. So when x is less than 1, let's just go ahead and find f prime. So I'm just going to find my critical point like I normally would, but I just know that I have this interval that I'm looking for between -2 and 1 because that's the only place where this graph is going to live on my for my piecewise. So I set f prime equal to 0 to find my critical point. -2 minus 2x equals 0. -2 equals 2x. X equals -1. So -1 does land between -2 and 1. So I am going to keep that as a critical point. Okay, so I do want to keep that as a critical point. Now, when x is greater than 1 for this second piecewise, if I set that equal to 0, I'm not going to get any critical point because 4e to the x minus 1, if I find the derivative of this, that derivative of this is just going to be 4e to the x minus 1 because that 3 goes away. And my slope of 4e to x minus 1 is always is never going to be equal to 0, because if I try to divide by 4, take natural log, this e to the x minus 1 is always going to live above the x-axis, so no critical point. So we only have to test our endpoint, -2, the critical point that we found here, -1, and where the two graphs meet, that's a critical point, 1, and then that also at 2, because 2 is the endpoint. Okay. So we're just going to take turns and insert these 4 points into the piecewise function wherever the graph lives. So if I can plug -2 into the first piecewise because that's where the graph lives, less than 1, and that's going to get me to 10. Okay. If I plug -1 in, -1 is also living on the first piecewise function. So -1 in for x, I get 11. Plug 1 in. I know 1 is a critical point as well because that's where the two graphs meet. F of 1 equals 7. And finally, f of 2 is with the last piecewise, 3 plus 4e to the 2 minus 1. So that's just going to be e. So now e is around 2.8. So if I just do a really rough estimation, 4 times 3 or 4 times 2-ish is 12. 12 plus 3 is around 14 and 15. So we know that between 14 and 15, let's say 14.5. And if I'm comparing all these numbers here, my highest is 14-ish, and my lowest is 7. So part C, find the value of the definite integral from 0 to 2 of f of x. I want to find the area under this piecewise function. Now, between 0 and 1, it's under the first curve, and then between 1 and 2, it's under the second curve. Right? So I can just do an integral notation. One integral to find the area from 0 to 1 under the 10 minus 2x minus x squared. And then from 1 to 2, it's under the 3 plus 4e to the x minus 1. Right, so this is takes a little bit longer because without a calculator, we got to do this by hand. So 10 becomes 10x, 2x becomes 2x squared over 2, x squared becomes x cubed over 3. Evaluate between 0 and 1, plug in 1 in for x, then plug in 0 in for x. I get all the way down to 26 over 3. And then this 3 to the 4x, e to the x minus 1, use substitution. This is still going to remain e to the x minus 1. 3 becomes 3x, though. power rule, u substitution, but e to the u is still e to the u. Plug in my upper and lower bound. 2 goes in first, 3 times 2, plus 4e to the 2 minus 1, minus lower bound, 3 times 1 plus 4e to the 0. 4 to the 0 is going to be 1. So it's going to be 6 plus 4e minus 3 minus 4. And that gives me negative 1 plus 4e. So this results in negative 1 plus 4e. This side results in 26 over 3. I just put them next to each other. You can leave it in this form. You can also combine further. All right, with the remaining time that I have with AB, I just want to kind of talk about the first steps. I think that's always the hardest part, right? To look at a problem and identify what's the first step, and once you can figure out that first step, usually we can kind of just move through the problem. It's always the hardest part to figure out, how do I start this problem? All right, so let me just at least want to highlight each of the first steps. So cosine of u, we should recognize, okay, this is understanding there's a little bit of chain rule here, just memorizing the rule for cosine of u is negative sine of u times u prime. And we just match that rule and follow the rule, and we get negative 2 sine 2x. Okay, remember the first 30 questions here will be non-calculator. Number 2, whenever I see a messy exponent, well, I always want to see if I can expand it, but that exponent is too much. I can't just do power rule, so I have to rely on u substitution. So my u value is the portion inside the parentheses. I go through my u value, u substitution, get my derivative to show up, get the x squared to cancel out, keep track of my coefficient, apply power rule. Once I apply power rule, bring back my original variable, and then the plus c. Number 3, if I see a limit approaching infinity, I know I don't plug in a real number here. I'm comparing degrees. But if I'm comparing degrees here, it looks like the degree in the numerator is higher than my denominator. But if you look, it's under the square root. So this is really x squared, because the square root of x to the 4th is x squared. But this 9 is also getting impacted. That 9 really turns into 3x squared. We don't care about the lower degrees. Those just cancel out. So if I just get that numerator cleaned up and I just get rid of the lower terms, I'm left with 3x squared over 4x squared. So that's a lot more clear that if we're doing infinity, we compare degrees. Degrees are the same. We take the ratio of the coefficients, so 3 over 4. Number 4, we have y equals x over x plus 1 to the 5th. We want to find the derivative. Now this is a function within a function. We really have to go through chain rule here, but then within chain rule, there's also that numerator denominator that's not easy to resolve. So I got to go through quotient rule again, quotient rule as well. So I got to go through a full 2 process here. I got to do outside derivative, which is chain rule. And once I get inside, I got to go through quotient rule. So outside derivative, parentheses 5th becomes 5 parentheses to the 4th. And once I get inside, I go through quotient rule, f prime g minus f g prime all over g squared. Now, the thing to keep in mind is that this x plus 1 is not just x plus 1. This is x plus 1 to the 4th. So that degree 4 and that degree 2 is going to cause the denominator to end up with a degree 6. So I think the best way to see that is if I separate my numerator and denominator, make it x to the 4th, x plus 1 to the 4th. And if I can see the 2 parentheses with the exponent above it, it's more clear for me to see, okay, I need to add the exponents. 4 plus 2, that gives me 6. And this just cleans up to be just 1. I'm just left with 5x to the 4th over x plus 1 to the 6th. All right, number 5, the need for trapezoid area. Make sure we know that. 1/2 width, height 1 plus height 2. And then we're looking for the amount of gallons in the tank at 9 hours. Okay, we have R of t, which is a rate. So to get everything up from a rate to that gallons level, we got to take the antiderivative. So initial plus displacement, W of 9 equals W of 0. We know W of 0 is 15. They tell us there's 15 gallons to begin with. And if we accumulate the gallons per minute over the 9-hour period using 3 trapezoids, then we're going to accumulate 52 gallons after in that 9 hours. So we start at 15, we add 52 gallons, we get 67. Number 6, slope of the line tangent. So we know we got to find y prime of -1. So y prime is u prime over u because of natural log of u. That's just the rule for natural log. Once we find the derivative, plug -1 in for x, and we get that cleaned up to be -1/2. Okay, which of the following is the limit infinite? So I'm just putting them all over each other and see which one convinces me where the numerator is higher than my denominator. So the first one, I'm not convinced because degrees are the same, so that's just 1 over 1. Here, my degree is higher than my denominator, so that's just 0. Here, 3 to the x over x cubed. I have an exponential over a polynomial. Exponential is going to grow at a fast rate than polynomial, so this one is our answer here. And this will go to infinity. This one, e to the x and e to the x, we can disregard the x cubed, x squared. These are lower than e to the x. So these are degrees are the same, just 3/2. And then here, natural log, same degrees, same family of functions. My ratio is just 3/2. So the only one that's going to go to infinity is that 3 to the x exponential over a polynomial. Number 8, recognizing the need for u substitution. So kind of, if you want to rewrite it first, as a parentheses. And then once you get the parentheses to show up, that is that's where our u value lives. So our u value is x squared plus 9. We find the derivative, which is 2x. Find dx over d over dx, or solve for dx, which is d over 2x. My x's cancel out, pull the 1/2 in front, but I got to do some adjustment here. This is not natural log. This is power rule, but power rule with some adjustment, right? If we want to do power rule, we got to bring that 1/2 up to the top. Now we can go through power rule. So use the 1/2 over 1/2, clean that up, bring back your original variable, plug in your upper and lower bound, and work this out by hand. We get root 25, which is 5, root 9, which is 3, 5 minus 3 is 2. Okay, we have a derivative f prime. On what interval is f decreasing? So we just have to go through a first derivative test. And we already have f prime, so we can jump directly into our critical points, creating our slope sine line, testing our slope sine line. Normally, if there's numerator and denominator, we want to look for critical points in both the numerator and denominator. So if I set the numerator equal to 0, I'll get 0, so that's critical point. If I try to set the denominator equal to 0, I will get no real number. I get 1 plus x squared equals 0, x squared equals -1, take the square root. I can't take the square root of negative numbers, so no critical point there. So critical point is at 0. I plug -1, I get positive. I plug 1 in, I get negative. Positive followed by negative. There is relative max here. Decreasing will be from 0 to infinity. Okay, easy problem if we understand that e is just a constant. It's like a 3. So 3 becomes 3x, so e becomes ex. E to the x is just e to the x, so that stays the same. E to the x plus ex plus c. Hold on a second, I'm seeing some questions here. Okay, I'll come back to them. So 11, which of the following could be the graph of f prime, the derivative of f? So this is the f graph. So I'm just going to create a sign line that mirrors exactly what I see here, because this is the f graph here. So I see a relative min here, I see a relative max. And I'm just going to mark that as -1 and 1 to make it easy for me to have something in place. So I know decrease, increase, decrease. So this is my derivative sign line. I'm going to translate this to a derivative graph. So what I can do is from that sign line, I know that I know ultimately my f prime graph is going to have these features, right? Slope is 0, positive slope, and negative slope. So my -1 and 1 are going to be my x-intercepts. Those are my slope zeros. And then negative slope, it's got to live below the x-axis, so it's got to be here, but it's got to connect to this point. Between -1 and 1, it's got to be above the x-axis, so it's got to go up and come down. And then to the right of 1, below the x-axis. So that matches best with answer choice B. Okay, area, find the area of the enclosed region. We do need to know what 1 over x looks like. 1 over x is a rational function that kind of has this shape about it like that. Okay. So if we know just the basic shape of the graph, we can sketch that from C. We know C is less than 1, but greater than 0. So it's going to be, we're really just trying to find the area of this region here. So the area is top minus bottom. Top is sitting at the 1 over x. The bottom is sitting at the 0. So natural log absolute value of x is the integral of 1 over x. Plug in my upper bound, lower bound. Natural log of 1 is 0 minus natural log of c. So, but even though natural log of 1 is 0, we just want to use log property to make it match the answer choice here. So it's just natural log of a minus natural log of b can be condensed to be natural log of a over b. So in this case, natural log of 1 over c. 13, we have arctrig derivative rule here. So arctangent's derivative is u prime over 1 plus u squared. So u prime is just going to be 1. The derivative of x is just 1, and then 1 plus x squared. That's the derivative of inverse tangent. And then we just do power rule for 2x to the 1/2. So 2x to the 1/2 becomes 2 times 1/2 x to the -1/2. Fourteen is a little bit strange. When we do integral problems or solving differential equations, it's usually pretty straightforward. This one, though, if we click our cross multiply here, separate our integrals here, we know 1 dy becomes y. The right side here, we're not able to solve this by hand, so we just leave it in this form. We know it's going to be the integral from 0 to x of x squared, or 0 to x of t squared, e to the t squared. Because we can't resolve this, not by hand. We have to leave this in this form. We don't really have an integral rule that can handle this, not with use substitution. So we leave it unresolved. But we do know that it's going to be this plus c. So if we have it in this form, we can still solve for c, because if I plug 0 in for x, that's going to wipe this out. Bound from 0 to 0 will still be 0. So I get 2 is equal to 0 plus c. 2 is equal to c. So if my c is equal to 2, I just put that in here, but this is unresolved. So we have to leave it in that form.
I have a question.
Yeah.
So do you have to put like the t at the end, like dt or t squared, or can I just keep it x?
Usually, if you want to do an integral, and if your upper bound is a variable, and there's a variable in your expression, they should be different variables.
Okay.
So we're just matching with this form here, but it could be e to the x, and then you could put like y squared over dy, y squared dy. They just decide to use t. Okay, this is just understanding what first theorem is going to do to this. We know that if f of t is the rate, we know the integral of the rate, which is turned into uppercase f minus uppercase f of 4. And if lowercase f is the rate of the water evaporation, then we can let uppercase f be the amount of water evaporated in terms of liters. So if we just use that notation, we can say, okay, f of 10 minus f of 4. And this is the amount of water in the 10th hour, amount of water in the 4th hour. So we can just be able to interpret, okay, this must mean how much water has evaporated between those time periods. (16) we want to find points of inflection. Points of inflection comes from the second derivative. So once you get to the second derivative, you factor and you solve, you get 0 and 3, but just be careful. We can't just say, oh, these are my x values, these have to be point of inflection. I still have to go through my slope, my concavity sign line, and test these subinterval and make sure that there's a change in sign. If there's no change in sign, that's not a point of inflection. So only point of inflection is going to be at x equals 3. 17 is just working out average value theorem by hand. 1 over b minus a, integral from a to b of f of x. We know 1 over x turns into natural log of x, plug in my upper and lower bound. And I'm just using my log properties here. This would be a acceptable solution if it was for response, but we're trying to make it match an answer choice here. So if I factor that 1/2 out, I can say natural log of 6 minus natural log of 4. And if I have natural log of a minus natural log of b, I can condense that to be natural log of a over b. And that 6 over 4 can be condensed to be, or reduced to be 3/2. Okay, this is pretty rare here. We see a optimization problem. Okay, so but the big picture with optimization, I know we didn't do much with optimization, but really optimization, you find whatever equation that will build that area or build that that unit or that whatever the equation that they're looking for. And then when it says maximum, all you do is you just find the derivative, set the derivative equal to 0 and solve for x. So basically, it's like finding critical points, like finding critical point, but under the umbrella of what they call optimization. So if we can somehow create the equation, find the derivative, set equal to 0, solve for x, that's going to be your solution. So we have 0.30 x0 x 1 over x squared and 3 1 over x squared. So basically indicate that we have these ordered pairs that form this rectangle. Where can we get maximum area? So let's build the area formula first. Area of a rectangle is base times height. We know the base is whatever the distance here is x minus 3, and the height is going to be 1 over x squared. Okay, so we build that area equation, base times height, get that cleaned up, get it ready for power rule, find the derivative. Like x to the -1 becomes -1x to the -2. 3x to the -2 becomes 6x to the -3. We set the derivative equal to 0, and then we just solve for x. So here I set them equal to each other. I cross multiplied. I factored the x squared out. X is 0. We know x can't be equal to 0 because that is clearly to the right of 3. And then so x equals 6 is going to be the better solution for us. 19, if we just go through power rule, we can just work this solution out and solve for x. So I set up my integral, go through power rule, t to the fourth over 4, plug in my upper and lower bound. Upper bound is 2, lower bound is x. I know it's equal to 0, so I can work backwards and figure out what x is. So this is 16 over 4, which is 4. 4 minus x to the fourth over 4. Set them equal to each other, cross multiply. The fourth root of 16 is plus or minus 2, because I'm taking anytime I take the square root, fourth root, and even root of both sides, there's always going to be a plus or minus that shows up. Okay. Number 20, working through point slope form. Finding tangent line equation. So if I want to find the order pair, plug power 4 in for x. We know that if I have power 4 to power 4, that's just going to be 0. So I know my order pair is 0. My slope is going to come from the derivative. To find the derivative, I'm going to go through a second theorem here. The derivative of this mess will just get it all the way down to sine squared x. Okay. And this is already my derivative, so there's no need to find the derivative anymore. H prime of x is just sine squared power 4. So sine squared power 4, if I pull that exponent outside, sine of power 4 is root 2 over 2. Again, unit circle value. Square that, we get 1/2, or 2 over 4. So you have your order pair, you have your slope, and then point slope form, and match your answer choice. All right, 21. Which of the following must be true? Here we have a bunch of order pairs, right? -1, -30, 0, 2, 3, 10, 5, 18. F has no critical point from -1 to 5. Well, looks like there could be a critical point at, well, right, for there to be a critical point, there has to be a y value of 0, right? Now, we don't see a y value of 0, but it doesn't mean that a y value of 0 is not going to show up somewhere. So we don't have enough information to say yes or no about the critical points from -1 to 5. F prime, so this is saying we're always guaranteeing a positive slope for part C between 1 and 5. Now, here, the numbers are increasing, but the graph could suddenly dip somewhere between and experience a negative slope that we don't know about, so we can't guarantee this is always true. This is saying concave down. We don't know the concavity at these ordered pairs. A lot of things can change. And then no point of inflection. The graph is always increasing, but there could be a point of inflection. We just don't know enough about this data. So second one, f prime of x equals 8. So can we guarantee a slope of 8 on the interval from -1 to 5? We have no f prime values, but we do know f prime is the slope of f. So if I can take my order pairs that's provided at the endpoints and see if that will give me a slope of 8. So usually that's where the slope is going to occur. If you're doing mean value theorem, usually they are pretty nice about telling you where to find that slope. But I've seen instances where you have to go hunting for that slope, which in this case wouldn't be too bad because there's only a couple order pairs. But we always want to test the endpoints that they gave us. So I'll plug in test order pair at -1 and order pair at 5. So I'll do 18 minus -30 over 5 minus -1. And that does give me a slope of 8. So this is what the graph could look like. Okay, so if my graph, if my average rate of change, if my slope between the endpoints is giving me a slope of 8, then the curve has to at least reach that certain steepness or slope of 8 as well, at least once. Okay, so this is what the graph could look like. So here's what we found, right? We found that the slope between the endpoints is 8. So if there's a steepness of 8 between the two endpoints, there's no way for the graph to not experience a slope of 8 somewhere along the curve as well. Doesn't mean they have to look like this, but this is just an example of what that instantaneous rate of change could look like compared with the average rate of change. (22) is a tedious problem because we have to take the antiderivative twice. So acceleration, and the integral of acceleration will bring us to velocity. We go through power rule, taking the order pair. Well, we can't plug in any order pair because we don't have any order pair at the velocity level. So we have to hold on to that C value. We go through power rule again. C becomes C T. So that C that's produced from the first antiderivative will become CT, and then it'll produce its own constant as well. So imagine this is +3, right? +3 will become +3t plus C, but instead it's plus CT plus C sub 2. Okay, so we clean this up, get that order pair. Now they give us two order pairs at the position level because if we plug that 0, 10, we can solve for one C value and then take that C value, update the equation, and use the second order pair to find the other C value. And then once we find that C value, we can update our position function. Then we find the velocity when the particle is at t equals 0. So we go back and find the derivative of position, go through power rule, back to velocity, plug 0 in, and we get 6. 23, we've done a lot of these differential equations. Cross multiply, separate the variables, natural log on this side, use substitution on this side, and then once we find our antiderivative, solve for y, solve for c, and then find your specific equation. (24), we need to recognize the need for related rates. We have per hour, all these units of time provided. Our volume is r³/3. Circumference is increasing, so that's dc dt. When the circumference is 8 pi, so that's c equals 8 pi. Find the rate of change of the volume of the pile. So we know v is 1/3 r³. We find the derivative, v becomes dv dt. We go through power rule here, r becomes dr dt. Clean that up, and we're just going hunting for variables that we can plug in. So we're trying to find dv dt, so that's a variable that's the unknown. We know the circumference is 8 pi, so from that information, we can work backwards with the equation and solve for r equals 4. So if r equals 4, I can plug 4 in for r. And I also know that circumference is 2 pi r. I can find dc dt. My dc dt is 5 pi. It's given to me here. And I can use that to solve for dr dt. And if I have dr dt, I can plug that back in and solve for dv dt. So this one's a little bit, has a lot of these kind of puzzle feature to it where you have to find one thing, then another thing, and eventually get back to your answer. 25, if I see a limit problem that's messy, I'm always going to think maybe this is L'Hopital's rule. So plug 0 in for h, and I'm able to get it down to 0/0. So that gives me indication I can go through L'Hopital's rule. So find the derivative of the first term. That will just give me e to -1 minus h times -1. E to -1 is just a constant that will go to 0. H becomes 1. Replace all the h's with 0, and I'm getting it all the way down to a real number here, (1/e).
Do we have to know squeeze theorem for the exam?
Squeeze theorem is technically on the yeah, it's one of our units, one of the topics that is considered valid. So I'll just show you real quick what squeeze theorem is, but it's usually pretty straightforward. Let's say I had, and they always have to establish this relationship that that there's 3 functions and there's going to be one that's going to be between. Okay. And let's say they gave you information about the outer ones, but they don't give you enough about the inner ones. So let's say they say, oh, the limit as x approaches 1 of f of x is equal to 4. Okay. And then they say that the limit as x approaches 1 of h of x is also equal to 4. So the way that squeeze theorem works is if the outer limits are the same, and you know the middle function has to live between, then this middle function gets quote unquote squeezed between these two numbers, and there's no choice but for the middle to also share the same limit, even though we don't have a direct data about g of x. That's basically squeeze theorem.
And then do we have to know like integrals like the integral of tangent or the integral of arcsine? Or
Very unlikely.
okay.
Yeah, very unlikely. Let's see. This is 26 here. Let f be the function given by f of x equals x cubed plus 5x. For what value of x on the closed interval does the instantaneous rate of change equal the average rate of change? So if you see this spelled out for you, this is really seeing if students understand that this is basically mean value theorem. Instantaneous rate of change is f prime. Average rate of change is the slope between the endpoints. So we just basically have to go through mean value theorem. So mean value theorem, we take our x values, insert into the order pair, into the function to get our order pair. So we find f of 1, we find f of 3, we find the slope between the endpoints, and that's our average rate of change. So no calculus here, we're just doing order pair and slope. So there's my average rate of change. Change in y over change in x. My instantaneous rate of change comes from the derivative, so I need to find f prime. F prime is 3x squared plus 5x. So I have my instantaneous rate of change information. I have my average rate of change information. I'm setting them equal to each other, and I'm solving for x. '27 is really convoluted, but I'm just going to kind of highlight the main steps, and then you guys can work it through later. The idea is that we have to go through chain rule. E to the u becomes e to the u times u prime, but then within that xy, we got to go through a product rule and implicit because there's y hidden in there. So e to the u, e to the xy becomes e to the xy times, and then u prime is the root of xy. So f prime g plus f g prime. Y squared becomes 2y dy dx. E is a constant, goes to 0. 4 is a constant, 4 goes to 0. And if I distribute this through, I can get dy dx. And once I get dy dx, I can plug in my 1/2, my 2, and get my slope, and then clean that up and get it all the way down to 4e over 8 minus e. This is one of those problems where if you see a problem like this on your AP exam, you know, like it's good to kind of map out what you think you want to do, but you don't want to spend all your time doing this before working at the other problems, right? You know, like this, it's good to work this problem through, but you also want to, just have a keep in mind that that there's a time and there's a time component here, right? So it's probably not worth spending 10 minutes on this if you can, when that 10 minutes can go into at least working through the problem. I don't want students to be stuck on one problem and not even have a chance to work on the other problems because they're spending 10 minutes on a really long problem. So yeah, so just really keep the time component in your head, or keep looking up and make sure that that if a problem is going to take too long, circle it, come back to it, but don't work on it until you've at least seen the rest of your test, because maybe there are some easy problems that you can quickly get through and then come back to this one. Right. This is 28, derivative of inverse at a point. We walked through this where I like to create the chart to help organize my information. I know my order pair at the function level will be flip-flopped. And if I can find the slope of the f graph at a point, then I can use that to find the slope of the inverse at the corresponding point. So the nice thing is they tell you g of 3 equals 1. So if g of 3 equals 1, then f of 1 equals 3. That's the relationship we're going to always have between a function and its inverse. We don't have the g data, but we do have f function to work with. So if I can find f prime of x, find f prime of 1, then whatever the slope is, that slope is going to lead me to the slope that I'm looking for. So if I get a slope of 5, I get 1/5. If I get a slope of 7, I get 1/7. If I get a slope of 6, that's going to lead me to 1/6. It's always the reciprocal. Don't change the signs, just change the order of the numerator and denominator. Okay, I'm running out a little bit over time here, so let me just highlight just maybe like 5 or more problems from the calculator section of the A/B test. 78 with a calculator, so it's nice that we can graph this e to the x, y equals e cubed, and recognizing that, okay, this is my shaded region, and my dotted line is down here. So there's a gap between my dotted line and my shaded region. So I go top minus bottom. I know it's got to be washer method. I got to draw 2 radius. My radius has to extend from my dotted line to my boundaries of our shaded region. So this is my big R. This is my little r, top minus bottom. So e to 3 minus -1. E to the x minus -1. And I set up my bounds from 0 to 3. And then big R squared minus little r squared. 79. The rate at which people are entering is f prime. The rate at which people are leaving is g prime. So the maximum number is when we have f prime minus g prime equal to 0. Right? So the rate at which people are coming in and people are leaving, once they are equal to each other, we know that's the maximum, because after that point, g prime is going to rise above f prime, and the number of people in the museum is going to continue to decrease. So we basically want to set f prime minus g prime equal to 0. We're going to graph this mess and then look for the x-intercept. Product rule. Yeah, I mean, if it's calculator section, you can really expect them to give you a derivative graph, and then you graph that derivative graph, and they're going to ask you a bunch of information about the original function. So if you graph f prime, you know your x-intercept is going to be your potential max and min. You know that your peaks and valleys are going to be your points of inflections. So find all those corresponding points, and then create your slope and cavity sign line. And if you can read off of your sign line, then it's easy to narrow down which answer choice will be appropriate. Same thing here. F prime below the x-axis is decreasing. Okay, so 10 minutes over, but yeah, there's one more thing that I want to make sure I do with you before I let you guys go and have switch over to BC, is how do we handle absolute value functions? Okay, like this, right? So if this were to show up, it'll be non-calculator, and we got to be able to know how to do this without a calculator. The way you do this is you graph it, and once you graph it, you're going to have 2 triangles, and you're adding up the triangles, and that's going to be your depth interval. So first thing, recognize where that vertex is. So absolute value of x minus 2 means there's a vertex at 2 because whatever causes the absolute value to be 0 is where your vertex is. And then if that's where your vertex, you're going to extend that vertex and the V and go as far left and far right as your bounds will allow. So we're going to go to -1 and we're going to go to 4. Okay. You should be able to draw a vertical line to the graph, and then you should be able to see 2 triangles that pop up. And that's it. You're just trying to find the areas of those 2 triangles, and that will give you the value of this. Right? So I know the area of my triangle is 1/2 base times height. Right? If I plug -1 into this function, because this graph is absolute value of x minus 2, I can find the y value, right? So if I plug -1 in for x, -1 minus 2 is -3. So this order pair is -1, 3. So 3 is the y value, or the height of my triangle. And my height here is also 3. So 1/2 base times height. That gives me the area of my first triangle. Second triangle, if I plug 4 into the function, 4 minus 2 is 2. So that gives me a height of 2, a width of 2. So 1/2 base times height. So 9/2 plus 4/2 equals 13/2. All right. Okay, thanks for answering the questions in the chat. I haven't been reading it. Okay, so I'm going to switch over to BC. So if you guys have any other questions, I'll be available tomorrow morning before your AP exam. And you can also send me questions over Remind. I'll try to answer them as well.
Thank you, Mr. Yang.
All right, good luck, guys. Okay, I'll start with FRQs. Thanks, guys. Good luck tomorrow. I'll start with FRQ. I'm going to skip BC1. I think that's pretty straightforward. Yeah, that's just entry in the calculator. Yeah, I'll go over BC4 and BC6, and we can go to multiple choice. Okay, let R be the region bounded by the graph of e to the negative x, below by the x-axis, on the right by vertical line x equals m. Find the area of R in terms of m. So we know we're going to go from 0 to m under the graph e to the negative x. So we just go through our process, use substitution, u equals negative x, derivative is -1. Make our substitution, and e to the u. We're left with negative integral of e to the u. E to the u is e to the u. Replace the u with negative x because that's our original variable. Plug in my upper and lower bound, m in for x, then 0 in for x. Careful, again, if I ever see 0 in my bound, I'm always double checking and making sure that that there's nothing left over. In this case, there is something left over, right? 0 in for x, e to the 0 is 1. So minus -1 is +1, e to negative e to the negative n plus 1. That's going to be my area in terms of m. Part B really is just the washer method. They inserted a B topic into this FRQ here. So we have e to the negative x from 0 to m. We're rotating about the line y equals -3. So we do top minus bottom, top minus. We know there's a gap, so it's washer method. And we just have to find our big R and little r and insert into our washer method formula. Part C, find the value of the real number k is greater than 1 such that the integral from 0 to infinity of k to negative x dx equals 2. So we got to think of k as a real number, like 3 or 5 or 6. And if that's the case, then a real number raised to a variable, that is an exponential function, base a, right? So if we're going to recall, this is one of our integral rules for base a. Integral of a to the u is a to the u plus c. It looks a lot like e to the u, but there's a conversion that happens, 1 over natural log of a. So we'll just treat k like we would a, it's just some constant. Okay, so we do the integral from 0 to infinity. We know it's going to be improper integral here, but we're just going to go through our process, go through u substitution. We know it's going to end up being a to the u with a negative in front. So the rule for a to the u is 1 over natural log of a. So instead of a to the u is k to the u. So 1 over natural log of k with a negative in front times k to the u. Replace the u back in terms of x, plug in my upper and lower bound. B goes in for all the x, and then 0 goes in for x. So if we think about what's happening here, if b is approaching infinity, that means my denominator is getting larger. My denominator is getting larger, my overall values, fraction is getting smaller, so it heads towards 0. K to the 0 is 1, negative 1 over natural log of k. Two negatives become positive. 1 over natural log of k equals 2. They tell us that our depth integral is equal to 2, so that is our pathway to solve for k. So natural log of k, 1 over natural log of k equals 2, which means if I cross multiply, natural log of k equals 1/2. Raise both sides with e as the base, I get k is equal to e to the 1/2.
Wait, so if you had a problem where it said like the integral from -1 to 1 of 1 over x dx, like how would you go through the limits and?
Oh, you're asking about a different scenario, right? Or you're
Yeah.
asking, okay, yeah. Right, so like this one, right?
Yeah.
Yeah, this one, I'm glad you mentioned this because this is one where, if we're not careful, we'll just go through our normal process and not even think about, oh, there's something strange about this problem. So if we see this one, we really have to kind of look for it. Like this looks a little bit too easy. There must be something that is that's getting that's hidden. And the hidden thing is always look at the bounds in relation to your denominator and look to see, wait, is there a vertical asymptote that's breaking this up? And there is a vertical asymptote, right? There's a vertical asymptote at x equals 1. And because that vertical asymptote, we can't just think of this as a straight up integral problem. We have to split the
X
problem.
equals 1 or?
Sorry, 0. Sorry. Yes, there's a vertical asymptote at x equals 0, and we have to split the problem up on both sides of our vertical asymptote. So we have to think of this as, okay, integral from -1 to 0, and then from 0 to 1 over x. And both of these will require their own one-sided limit, right? Because we can't reach 0 because those are asymptotes, but we can get close to 0 from both sides. So this one would be on the left side of 0. So limit as b approaches 0 from the left side of 0, from -1 to b of 1 over x dx. And then separately, approaching 0 from the right side of 0, because this is on the right side of our asymptote. Okay, so we'll go through our process separately here. We know this is going to be natural log of x, so natural log absolute value of x, evaluate between -1 and b. This one. So here, natural log of b, what's happening here? So if I just think about values, like approaching 0 from the left side of 0, so that could be -0.1, and then -0.001, -0.00001, right? So what's happening? Well, if you think about our natural log graph, if we're getting closer and closer towards 0, our natural log graph, natural log of 0.001, 0.0001, it's all headed down towards -infinity, right? So this is going to diverge to -infinity, right? Because maybe this is 0.1, then 0.01, then 0.001. So as we get closer to the y-axis, as we get closer to the y-axis, our y value jumps to infinity. So if one diverges, we don't have to test the other one. The other one is going to, I mean, the whole thing will diverge.
And I have one more question. This is a little bit different, but like normally if there was a limit as x approaches infinity, like I would compare the degrees and take action based on that. But what if it approaches -infinity? Like, what do I do then?
I'm also comparing degrees still. Like if it was
Oh,
like
is it the same
X,
process?
it's the same process, yeah.
Oh, okay. Okay.
The only thing you got to worry about -infinity is if the degree is higher. If the degree is higher, you know that it's either positive or -infinity. So you actually have to test like a -100 and convince yourself whether it's positive or negative to decide between the positive or negative infinity. Like you'll test like a -100. Because you know if the degree is higher, it's either go up or go down. You just have to decide which way is it going.
Got it. Thank you.
Okay, PC6. Okay, so we have our Taylor polynomial, fourth degree, 3 minus 6x squared, 5x cubed, 2x to the fourth. Find the third derivative at 1. Now, I'm just going to remind us what our Taylor polynomial series formula looks like. It's nth derivative evaluated at c over n factorial times x minus c to the nth. So anything dealing with the third degree, I'm just going to fill that in, right? So I'm going to say third derivative evaluated at 1 over 3 factorial times x minus 1 to the third. So this whole thing is what my third derivative would have to look like, right? So third derivative 1 over 3 factorial times x minus 1 cubed. Now, if I set this, if I looked at this, right, it's only really asking me for the numerator portion of this coefficient, right? It's the third derivative valued at 1 over 3 factorial. We know that that's equal to 5 because that 5 is associated with that whole thing. So if I can set up this equation, then I can figure out what the third derivative value at 1 is going to be. So 5 times 3 factorial, that's 6. 6 times 5 is going to be 30. Part B, does the graph of f have a relative max, relative min, or neither? So I know that relative max, relative min can come from, I can go through second derivative test. But first, let me just see what happens if I were to do f prime of x. F prime of x would just be negative 12x, 12x minus 1 plus, okay, there's more degrees here. But if I were to plug 1 into f prime, I would get 0, right? Because if I plug 1 in for x, I will get 0, and everything else will 0 out as well, right? So f prime of 1 is 0. So we know there's a slope of 0 at x equals 1. That we know for sure. Now, how do we know whether this is going to be a relative max, relative min? Let's look at the second derivative, right? So f double prime would be negative 12 plus 30 times x minus. So imagine we found f prime already. And if I want to find f double prime, it'll become negative 12. I'm sorry, this is f prime. So if I want to find the second derivative, it would be negative 12. This goes away, plus 30 times x minus 1. That's the higher degree. But if I were to replace 1 and for all the x's, that will drop out. I'm just left with a negative 12. And that negative 12 for my second derivative would indicate, okay, this must be concave down at 1. So if I have this information of slope 0 and concave down, that's allowing me to use second derivative test and say that a concave down with a slope 0 behavior can ensure that there must be a relative max at that point. So it says, let g be the function defined by the integral of f of t. Find the third degree Taylor polynomial for g. Now, what I want to do with g is I want to take the integral of f. So I want to end up with a degree 3. So if I want to end up with a degree 3, that means I only need degree 2 at the f level because I know power rule will make everything rise. So I'm just going to take what I have at the second degree level. So I'm not even going to worry about that third degree. Just worry about that second degree, because once I take the antiderivative, this will rise up to degree 3. And this is too high, right? 3 will go to 4, 4 will go to 5. So I'm just going to say 3 minus 6. I'm going to use t because I'm going to evaluate my upper bound in terms of x. Oh yeah, and they say f of t here. So 3 minus 6, t minus 1 squared. I'm going to go through power rule. 3 becomes 3t. I can go through u substitution, but nothing's going to come out of it. So I can think of this as 6u squared, 6u cubed over 3, replace the u back in terms of t, plug in my upper bound and lower bound. I get 3x minus 2 times x minus 1 cubed, minus lower bound, I get 3 minus 0. So g of x is this. Once I have my g of x equation, I'm going to use it to approximate g of 1.1. So plug 1.1 in. Now, this is without a calculator, so you can leave your answer in this form. You probably don't want to spend your time trying to clean that up. Just leave it in your unsimplified form. Part D, let h be the function defined by h equals f prime. So if h equals f prime, we can build our f prime. And then find f double prime. And then plug in 1. And if I plug in 1, I get 30. And if my second derivative value at 1 is 30, that means it's concave up. And I know that if something is part of a concave up graph, that can't be a point of inflection there. It's got to at least either be 0 or undefined in order for there to be a point of inflection. If I get a positive or negative number, then that's concave up or concave down. That can't be a point of inflection. So no point of inflection at x equals 1. I'm going to flip through the multiple choice, seeing if anything stands out that's out of the ordinary. Yeah, I would say, if you see an integral with trig and a function, sometimes it's u substitution. So I would always try u substitution first. And if that doesn't lead you to something that feels manageable, then we should be able to do integration by parts. I know some of my students, they see, I know they would jump into integration by parts without first checking u substitution. So make sure that you check u substitution before you do integration by parts. So for instance, if I had a problem that was this integral of x sine of x squared, this one would not be integration by parts. This one would be u substitution because your u value of x squared can handle that x here. All right, so always try u substitution first. If that fails, then at least you have this as your IBP or tab method as your safety net.
Can I ask a question on page 60 of the multiple choice?
Yes, page 16.
60.
Oh, page 60. Let's see.
Oh,
Is it packet 6?
I have the packet 6.
Oh, okay.
Yeah, part D on question 4.
Yeah. Yeah, we got to do IBP here. Yeah, it's kind of tricky because we don't know, like, how do we know what's our u value, what's our f value, what's our g prime. Let's see. X. Yeah, I wish we could do time method with this, but nothing is going to get that cleaned up. There might be a way using time method. Yeah, I may have to look at this a little bit, and send this because I'm not following this solution key here. Was that where you're getting stuck as well? Seeing what
Yeah, I got stuck there.
yeah. I wonder if it would be better if we let the f be e to the x so that our f prime could turn into f. But yeah, let me work on that a little bit later. See if I find anything, I'll send it to the group.
Okay, no problem.
Mm. Everything seems pretty manageable. Oh, did you guys look at 88, page 25 here? This one was stumping me because it didn't quite make sense initially. I had to look it up to kind of get some ideas as to why the answer is 3. So this one, okay, the value limit as x approaches 0, f of 1 minus x squared is. So we know the limit is what happens as x approaches 0, right? What happens when x approaches 0? And is there a consistency? Is the one-sided limit in agreement? If it is, then that should be the limit. So when x is close to 0, 1 minus x squared is always close, but approach 1 from the left side because value is always smaller than 1. So I think the easiest way to demonstrate this problem is let's just think in terms of one-sided limit. Okay, so if we're approaching 0 from the left side of 0, so let's say negative 0.1, and then negative 0.001, and then negative 0.0001. As we get closer towards 0, let me just demonstrate what that could look like. So if I were to choose like negative 0.1, right? Negative 0.1 in for x will be 1 minus 0.1 squared, which is maybe something like 0.99, right? 1 minus a number that's really, really small will be a number that is to the left of 1, but really close to 1, so 0.99. So if I do f of 0.99, f of 0.99 is maybe 2.8, right? I'm just for demonstrative purposes. It's close, but not as close as it could be. Now, let's choose negative 0.001. 1 minus 0.001 squared is going to be even closer, also coming from the left side. What f of 0.99999, which is even closer. So f of 0.999 is 2.9, right? And if we keep choosing values even closer and closer, that y value is getting closer towards 3, right? 2.9, 2.999, 2.9999. Okay. Now, if I plug 0 in, f of 0 or f of 0 will be f of 1. F of 1 is 2. But we know that a limit doesn't care about that ordered pair. It cares about the approach from the left and right side. So let's choose a value that's relatively close to 0 from the other side of 0. So if I plug in 0.1, 0.1 in for this expression, 1 minus 0.1 squared is still f of 0.99. So it's still talking about this side. That x squared is forcing every negative number to still always come from this side. So I'm still getting 2.8, right? And then f of 0.0001 is even closer, f of 0.999, and it's still 2.9. If you look at these numbers here, 2.8, 2.9, 2.99, 2.8, 2.9, 2.99, we can tell that these numbers are getting closer towards 3. So that's why the limit, even though it's approaching 1 from even though we're only looking at it from the left side, is because any decimal value we choose is that x squared is forcing it to always come from the left side, and that's why the limit is equal to 3. That one was a little bit strange. Notice that there is a cone problem, related rates. A logistic equation, being able to see the different variations of it. And sometimes it's just identifying what each of the values represent and then plugging in and see which one is actually going to be a true statement. So, understanding the parts of a logistic equation and being able to, sometimes it's just kind of like a verifying problem. Okay. Yeah, outside of that, I don't really see anything that really is surprising on this one. So yeah, I definitely will look at one of us mentioned that English by part. That was a little bit strange. So I definitely want to look at that and see if I can arrive at the answer that they got. What else do you guys want to look at?
Packet 6 and trying to find the problem. Page 61. For 6a, how do you determine the general term based on the derivative they give you? The series part is easy. It's just the general term.
Oh, from here to here?
Yeah.
Okay, so we're okay with the alternator here, right?
Yeah, but like, what's the
And
difference between -1 to the n or -1 to the n plus 1?
there's really no difference. I mean, there is a difference. It's just making sure that when you test them, that the negative and positive are lining up with your specific term. So you can either adjust it to be -1 to the n versus n plus 1 versus n minus 1 so that the negative and positives are going to line up. So n plus 1 will be the same as n minus 1. But it'll be different than -1 to the n because then the signs are not firing at the same time. Um, so that could be n plus 1 or n minus 1. That wouldn't affect anything.
Okay, I agree with the alternator.
Oh, your question was just about the alternator.
It wasn't about the alternator. It was just like the rest.
Oh, the rest. Okay, so you're okay with the alternator.
Yeah.
I think recognizing that your exponent is always going to be 1 degree higher than your denominator, and then just creating a relationship that will work. So that's why there's an n minus 1 to ensure that when there's a 2 up here, there's going to be a 1 below. When there's a 3 up here, there's going to be a 2 below.
But like for that term x, just x, the denominator can't be 0. So I don't like it works for the rest of the terms, but I don't know like the first two terms.
Oh, and we don't have to worry about them because they've already stated those are special cases.
Okay.
So then this is going to build starting at 2, but we have special cases for the first 2 terms.
Oh, that makes a lot of sense.
Can I also ask a question on packet 6?
Sure.
On page 33, number 82.
This one here.
Yeah, I just don't really get how you know that C is going to be like higher.
Oh wait, hold on. How C is going to be what?
Because I don't really get what the answer is saying.
Oh, I see.
Like I
Okay.
get why all the other ones are false, but I don't really understand that. The correct one.
I see. So I think this is saying is that if you have a closed interval and the function is continuous, I can find a value C where I can create a maximum value. That maximum value is guaranteed to be higher or equal to any other point that you can find on that function on that interval. So it's just saying that I can guarantee to locate an absolute max somewhere on that interval.
But that's like assuming it's increasing, like the function's increasing.
No, doesn't have to. It just says that f of c could be here, right? F of C is greater than any x value on f of x. So that could be an f of C. No, this could be an f of C. And that could be an f of C, right? There's a point C that is higher than any other point, or at least equal to any other point that I can find on the function.
Okay, now yeah, it makes sense.
It's just a really like convoluted way of saying yes, there's going to be an absolute max somewhere on that interval.
So if you know that you can make an absolute max there, why would the derivative like f prime c not equal 0?
Oh wait, oh, this one here. We can't guarantee that there's an f prime of 0 because maybe the graph is, maybe the graph doesn't, it's continuous, but it may not be differentiable, or it may just be increasing the whole way through. So just from the fact that we know it's a continuous function, there's still a lot of unknowns about the graph, right? You can create a bunch of scenarios where it says which following must be true, right? I can create a graph where it's continuous, but it's not going to have a slope 0. Any of these, these are situations where I'm not going to get a slope 0.
Is
But I
option
think,
C just extreme value theorem?
which one?
Like, is option C just extreme value theorem?
It's just extreme value theorem, but finding absolute max. It's just the absolute max component of extreme value theorem. So if continuity is the only condition that I have, then yes, then I can do EVT. But I can't do IVT. I can't guarantee an x-intercept. I can't do mean value theorem, and I can't do Rolle's theorem either. Not with just continuous being the only condition that's given to me. Does that answer your question?
I think so. But for EVT, do you not have to do like find critical values? So then
It is, yeah. I mean, if we have to find the number ourselves, then yes, we got to go through it. But all this is saying is that you're guaranteed to find an absolute max. That there's an absolute max that's gonna exist. Now the process that we go and find that absolute max, we got to test endpoints and critical points. But all this is saying is that yes, we can guarantee that there's an absolute max. That's all it's saying.
okay, so it's just like testing you on the conditions. Of
Yeah,
the test.
really. Yeah, just testing us on the
Okay.
condition. It's not.
Okay.
It's not solving the problem for us.
Okay, thank you. That makes sense.
Page 2, question 6.
Yeah, some students had questions about this. I was looking this up, and the only explanation they gave was that this one here, right?
Yeah.
Okay. I think the only explanation they gave was that my f prime, sorry, my f prime is made up of g of x, and g of x is this alternator. So my f prime has a component in the numerator that keeps increasing and decreasing, right? and the slopes gets is positive slope followed by negative slope. And the component of positive and negative slope is going to make it where I can't guarantee that every single b sub n plus 1 is going to be greater than b sub n. If there's even one instance where my subsequent term is not smaller than my previous term, then AST breaks down. So the fact that I have a positive slope followed by a negative slope, because of the positive and negative values, it's causing this condition to break down.
Okay, so like when it's oscillating, there's no like trend as in increasing or decrease. You can't like say for sure.
It's not the oscillating part. It's the fact that this f prime is going to have a positive and negative slope.
Mm-hmm.
So if my f prime is positive and negative slope, that means my value is increasing and decreasing. If my value is increasing and decreasing, then it's no longer always decreasing.
Okay.
And then also, for alternating series, every single absolute value of my subsequent term has to be less than the previous term.
Less than or equal to, or less than? Like...
Less than, has to be less than, yeah.
Okay.
Yeah, that's not I don't like that. I realized after I put it on, it's like, this is not a very easy problem. But they did that. But it was found in AP Classroom, and it was under the non-calculator section.
So like, when do I use Lagrange error bound versus like alternating series? Like, is it applicable on an alternating series, the Lagrange error bound?
Oh, never thought about that. When I think of Lagrange error bound, I think of it as the scenario, like a process that I would use if I can't do alternating series tests. That's what I think, but I never considered using the Lagrange error bound for something that is meant for alternating series. But
I think they do tell. Then like, they tell.
Yeah, I think. Well, I think the problem kind of gives it away when it's an alternating series, but I think it still works. I think with alternating series, it's always centered at 0, and it's always involving the first unused term. So that first unused term is just going to be n plus first derivative over n plus 1 factorial. I think it still works, but I think of alternating series. If I see an alternating terms every other term, and they tell me it's an alternating series, and that it converges by AST, then I just prefer to just use AST and just use that first unused term. It's a lot easier, a lot faster. I think Lagrange error bound, either they tell you or they give you a bunch of terms in the rule of sequence where you can obviously tell that it's not alternating in sign. So if it's not alternating in sign,
conditions for alternating series error bound, or I could just like do it straight away.
Say it again.
Are there any conditions to like use alternating error bound, or like can I just use
the only condition for AST is it does need to be an alternating series. You can tell by looking at the rule of sequence. There has to be an alternator, and there has to be the limit of my rule of sequence has to be equal to 0. And then the second condition, this is the one that we don't use as much, is that my a sub n plus 1, the absolute value of a sub n plus 1 has to be less than a sub n. So every subsequent term has to continually decrease. So for instance, it needs to be like...
Oh, basically it just has to converge.
Yes, it's converged, but it can't all of a sudden, like for instance, if I had -9 followed by, 8, then -6, then 4, then -2, then 1/2. This is fine, right? The approach is 0, and the absolute value of every subsequent term is less, right?
Yeah.
But if I had, let's say, 9, then -8, then 1, then -4, then 0, then, or let's say
The
this is
rule
like
breaks.
1/2. Yeah, so technically it is eventually headed towards 0, but it breaks down here. Even though this is less than this, the absolute value of this is not less than this. So if it breaks down, we can't use AST.
So so this one diverges.
Yes, it would diverge because it would not fulfill this condition. But if you had a problem like this, it would just be like a one special case. You wouldn't be asked to. Yeah, you're right. This would not
Usually
be
they give a converging.
Yes, they'll give you a converging one, and then the giveaway is when they give something like this, right? When they have the absolute value f of 1/2 minus or something like that, right? This is an indication that there's an error bound involved. They want you to use error bound, whether it's Lagrange or alternating series test. This is the kind of the giveaway.
It doesn't matter which order the f and the...
It doesn't matter because it's the absolute value, so it's always going to come
right.
out to be the positive difference between them.
And also, is root test unlikely to appear, or unlikely?
Yeah,
am I unlikely to have to use it?
Yeah, it's unlikely. Yeah.
Okay. And then one question. This is more of an AV topic, but I've seen I can't remember. I've seen a problem somewhere where there's a limit of a composite function, and then they give the graphs of the composite functions, and then there's one-sided limits, and it's kind of confusing.
I don't know if I have that problem on top of my head. You may have to send it to me. I'll find it. Let me know.
I think I found it. Page 57, question 34. That one.
Yeah, this may be similar to that previous one where if we really want to find the true limit, we really should be looking at the approach from the left and from the right. Let's see if that will answer the question. Limit. What is that approaching? Is that approaching -2?
Yeah,
This
the
is-
inner approach is -2.
2, okay. G of -2. (2.1). So if I played with numbers close to 3, like I tested 2.9, for instance, right? So if I plug 2.9 in for x, it'll be f of 2.9. F of 2.9 is getting closer towards towards -2. Yeah, -2, right? It's getting close towards a y value of -2. So then g of -2 is equal to -1. But if I do 3.1, 3.001, 3.0001, f of all those values are getting closer towards -2 as well from the other side. And then g of -2 is also -1.
So I just have to like test both sides.
Yeah, test both sides. Yeah. So I think anytime you have a weird limit problem, I think they're trying to get you to test from both sides and see where their approach is rather than the actual value at that point.
So like then for the second limit on like on the actual multiple choice packet, why did you put as x approaches -2 from the left?
Because it ends up always being from the left, because no matter what decimal value I choose from the left or from the right, that x squared is always causing a positive number to appear. And then 1 minus a positive number is always going to be to the left of that target point.
Okay. And then I don't have like an example for this, but like how do you do an arctangent integral problem? Like you have to do some u substitution and then get into the form. Like I have to complete the square at the bottom. It's just like the u substitution part that.
Oh, okay, yeah. Okay, so this one here. Okay, we know what goes in there is b over 2 squared. 4 over 2 is 2. 2 squared is 4. Okay, so we're trying to get this to fit into our integral rule here. Here's our integral rule for arctangent.
Can I remember that?
So my u value is x minus 2. But I do need to get that second set of parentheses to show up. Okay, these are the same things, right?
Yeah.
Okay. So my a is √5. du over dx equals 1.
Dx equals du.
Right, dx equals du. So if I if I try to get this all in terms of u and du, it'll look like this.
Oh, you push the 3 out. That's the
Yeah.
part.
And now I'm just gonna follow the rule and put everything back in place. The 3 is gonna be there, 1 over a, so 1 over root 5 arctangent of u over a plus c.
Okay, that makes sense. And then like if it's a linear decomposition, like one will work and the other won't. Is that how it'll be? If I had to decide between one of them.
Oh, got it. Okay, so you're saying between arctangent versus partial fraction decomposition.
Yeah, like
Yeah.
like
So yeah. If I can factor it, then I want to go through a partial fraction. If I can't factor it, and I have to go through complete the square, then I would do arctangent.
okay. That makes sense.
All right. Anything else?
Thank you, Mr. Yang.
All right. Thanks. Good luck. Get some rest. See you guys. Bye.